Welcome to Lecture 18, Section 4.3 of the text Elementary Linear Algebra by Ron Larson, 7th edition, Cengage Learning, Subspaces of Vector Spaces. This is Dr. Gilbert, Eyabi. Briefly, let's look at the goals of this lecture. Number one, we would determine whether a subset W of a vector space V is a subspace of V. And number two, we will determine subspaces of Rn, the n-dimensional space. Okay, firstly, let's start with subspaces of vector spaces. Definition. Number one, non-empty subset. That's the first condition W must satisfy. So a non-empty subset W of a vector space V is called a subspace of V when W is a vector space under the operations of addition and scalar multiplication defined in V. i.e., what that actually means is that W is a subspace of V if W is also a vector space. The relationship W is a subset of V, so it is called a subspace, just like a chief and a subchief. A subchief is a chief, it's just that he or she is under some other chief. And of course, W has to be a vector space under the same operations of addition and scalar multiplication defined in the larger set V. For example, let's look at this set right here. W equals the set defined by x1, 0, x3, where x1 and x3 are real numbers. Is this set a subspace of R3? Realize that W is a subset of R3, set of all triples. So to verify that this is a subspace of R3, we would have to go through all 10 properties to make sure they are satisfied. All the 10 axioms which we saw in the previous lecture, we have to verify that all 10 axioms are satisfied with W, with the standard operations. For example 2, we define W as the set of all ordered pairs x1, x2 such that x1 is bigger than or equal to 0, x2 is bigger than or equal to 0. Now, it's very important that you understand that definitions are very important in mathematics and how to read definitions. What does this mean? W is the set of all ordered pairs such that the first component is bigger than or equal to 0, the second component is bigger than or equal to 0, and each of these components are real numbers. So for example, -1, 5 is not going to be in W because the first component is not in W. Now if we go back to the first example, this is the set of all triples such that the first and the third terms or components are real numbers. It doesn't matter whether they're negative, 0, or positive, they are real numbers, but the second component must be equal to 0. So for example, 105 is an element in W. -1, 1, 2 is not an element in W because the second component is not 0. It's very, very critical that you understand how W is defined because we would need this definition to prove that things are subspaces and so on and so forth. Now let's go back to this second example. Now just looking at this and keeping your focus on the 10 axioms we saw for a vector space, would W be a vector space? Remember, one of the conditions I think condition number 6 is that it has to be closed under scalar multiplication, i.e. if u is in W, then alpha times u has to be in W. Now take your scalar alpha to be -1 and let x1 and x2 be positive numbers, say 1 and 2. Then alpha u would be -1, -2, which is not an element in W. So very clearly we can see that W is not closed under scalar multiplication. So obviously W is not a subspace of R2. Now, does that mean that each time we are given a subset of a vector space and asked to verify whether or not it is a subspace, we would have to go through all these 10 axioms? As a matter of fact, no. There are several of these properties, of these axioms, that would automatically apply to W, just given the fact that W is a subset of V. So there are just a limited number of properties that we would verify, and we shall introduce these in what is known as the Subspace Criterion, or the characteristics of subspaces. And here we go. The Subspace Criterion, or the test for a subspace. If W is a non-empty subset of a vector space, again I really insist on this, the first thing you have to verify is that W is not empty. So if W is a non-empty subset of a vector space V, then we say that W is a subspace if and only if the following are true. Number 1, U and V in W implies that U plus V is in W. Closure under addition. Number 2, U in W and C is scalar, then alpha U is in W, i.e. closure under scalar multiplication. So if you can verify closure under addition and closure under scalar multiplication and show that W is non-empty, then we conclude that W as defined is a subspace of the given vector space V. Now I'm going to put all 3 conditions together: W non-empty, closure under addition, closure under scalar multiplication, and this is the definition or the statement of the subspace criterion, which I would advise that you use. W, a subset of V, is a subspace of the vector space V if and only if condition number 1 that you have to verify, W is different from the empty set, is non-empty, and number 2, for every UV in W, alpha, beta in R scalars, alpha U plus beta V is in W, i.e. the linear combination of U and V would have to be in W. If you verify these 2 conditions, then you have satisfied the subspace criterion, and we can conclude that W is a subspace of our vector space V. Of course, if you want to go through all 3 properties, that's fine also. Show that W is non-empty, show that it's closed under addition, and show that it's closed under scalar multiplication. Example: which of the following subsets is a subspace of R3? Look at this subset right here. Which of these would be a subspace? So we're going to go through and try to verify the properties that we've just mentioned to see if they hold for A and B. Number 1, let's look at the first. Take alpha to be equal to 0, that's a scalar, and take U to be the vector x1, x2, x1. As a matter of fact, let me go back a little bit. Now look at W. How is W defined again? W is defined as the set of all triples whose first two entries are real numbers, and the third entry is the number 1. So elements like -2, 5, 1 will be in W, but elements like 0, 0, 0 will not be in W because the last component is not a 1. For B, how is B defined? B is a set of all triples where the first entry or the first component is a real number, the third component is a real number, and the second component is the sum of the first and the third components. So 2, 5, 3, would be an element in W. Okay, let's go back. Now, if alpha is 0 and u is x1, x2, and 1, then alpha u is 0, 0, 0, which is not an element in W, and therefore we conclude that W is not a subspace of R3. Remember, for it to be a subspace of R3, it has to be closed under scalar multiplication. For every scalar alpha, alpha u is supposed to be in W. Okay, let's look at the second example. Again, observe the second example. A set of all triples where the first component is a real number, the third component is a real number, and the second component is the sum of the first and the third components. So 1, 1 plus 2, 2, which is 1, 3, 2, is an element in W. Therefore, W is nonempty. So to prove that first condition, the condition that W is nonempty, you have to construct an example. You have to construct an element in W, an element that is clearly in W. Most texts would actually use the 0 vector as the element in W. It's usually much easier to verify using the 0 vector. So observe that the 0 vector, which is 0, 0 plus 0, 0, is in W. We could have used this, and this only proves that W is different from the empty set, and that's beautiful. Now, the second part of the criterion, we pick the vectors u and v in W, alpha and beta in R, and verify if alpha u plus beta v is in W. Now, alpha u is alpha times what u is, plus beta, that's what v is. Recall, u is x1, x1 plus x3, x3. Beta is y1, y1 plus y3, y3. Now, using the standard definition of scalar multiplication and addition of vectors, this would give us alpha x1 plus beta y1, the second component, the third component. Remember, if I have to show that this is in W, I have to show that I can write this in the form first component, third component, and the second component has to be the sum of the first and the third components. So I rewrite this in the form alpha x1 plus beta y1 plus alpha x3 plus beta y3, and observe that this is my first component, that is my third component, and the second component is the sum of the first and the third components. So I can call all of these my x1 wiggle, x3 wiggle, and this becomes x1 wiggle plus x3 wiggle, which is an element in W. Therefore, W is a subspace, and we can smile. Theorem: the intersection of two subspaces. If V and W are subspaces of the vector space U, then the intersection of V and W is also a subspace of U. So if my V is a subspace My W is a subspace. V intersection W is a subspace. Let's look at the proof. Proof. What are we actually required to prove? It's very important that you know what you want before we go for it. So number one, we want to show that V intersection W is non-empty. Number two, we want to show that if I pick any two elements U and V in V intersection W and any two scalars alpha, beta in R, then alpha U plus beta V would be an element in V intersection W. It's very important that you remember the two steps involved in satisfying the subspace criterion. Okay, so let's start validating these steps. Number one, the zero vector is in W and the zero vector is in V, since both V and W are subspaces, or as a matter of fact, vector spaces. So they have to contain the zero vector, and the zero vector is the ID element. So given that they are vector spaces, the zero vector must be in V and the zero vector must be in W. But that simply means that the zero vector is in V intersection W, and that means V intersection W has at least one element, i.e. it is non-empty. And that satisfies our first condition of the subspace criterion. Number two, let U and V be elements of V intersection W and alpha, beta be real numbers. Remember, I have to show that alpha U plus beta V is an element of V intersection W. U and V in V intersection W means that U and V is in V and UV is in W by the definition of intersection. But UV in W, alpha, beta in R, and V is subspace by the subspace criterion implies that alpha U plus beta V is in V. Similarly, U and V in W, alpha, beta in R, W is subspace by the subspace criterion, alpha U plus beta V is in W. But by the definition of intersection, if alpha U plus beta V is in W and alpha U plus beta V is in V, then we can conclude that alpha U plus beta V is an element of V intersection W. We have satisfied both conditions of the subspace criterion, and we therefore conclude that V intersection W is a subspace of U. In general, if VI's I from 1 to n are subspaces of U, then the intersection I from 1 to n VI is a subspace of U. What do you think about the union of the AIs, I from 1 to n? Thank you very much.